Greenland. A massive ice-covered island in the northern Arctic. A land of pristine waters, enormous glaciers, and ancient geology. And for some, the site of a hotly contested claim of the oldest signs of microbial life on Earth.
It's always when I go see some rocks and outcrops in the flesh, it's so much more eye-opening and informative than it is to read about them in papers. And absolutely the case with this one when I came to see them after that paper was published.
Meet Dr. Abigail Allwood, astrobiologist at the NASA Jet Propulsion Laboratory. Dr. Allwood is here in Greenland to investigate recently published findings of possible stromatolites, or microbial fossils, dating back to 3.7 billion years ago.
I very much doubted that interpretation, and I thought, well, we need to do two things. We need to put a paper out, and secondly, we need to do a workshop and bring a lot of people out here to also see what their opinion is, reach some sort of a consensus on what the right interpretation was.
Extraordinary claims require extraordinary evidence, and a finding like this requires further investigation. Dr. Allwood has gathered a team of astrobiologists and will now travel by helicopter into the wilderness of the Ishua Greenstone Belt.
So we're out here to study an outcrop that there is some controversy over. There is a group of authors that has made a claim that there are biosignatures in the form of stromatolites in these rocks. And there's another group of authors, I happen to be one of that other group of authors, that has refuted that claim. So we're out here in Greenland to study those outcrops in more detail and to try to get a sense of the geology that surrounds those potentially stromatolite-bearing outcrops and try to get a sense for what the ancient environment looked like at the time that those rocks were forming. The claim was such a big deal because if it proves to be true, then this pushes back the earliest signs of life in Earth's geological record by a couple of 100 million years.
It means that the window of opportunity for life to emerge doesn't have to be very big. Literally, as the last bombardment is occurring, that you can say that life can take hold. At least our one example that we have that life took hold. Go to Mars. It means that it only also had to maintain its conditions, its sort of cradle of life, its opportunity for life to emerge for that short period of time. It didn't have to sort of maintain it for a couple of 100 million years longer.
And when you go back to those very old rocks, they're usually altered and deformed, and it's very difficult to find those signs of life. But those are also the most interesting rocks to look at because we don't know when life originated on Earth, and we don't know what that earliest life was like. So the record that we have from geology is in these rocks that are very difficult to interpret.
Wonder which way I'm going to put it.
Sampling here in Greenland is, it's not all that different from sampling anywhere else. A geologist's tools are kind of the same no matter where you go. You need a hammer, a chisel, a little, hand lens to look at the rocks up close, field notebook, camera, and, you record your observations. And when you think you've zeroed in on a piece of rock that might be worth taking back to the lab, you get your trusty rock hammer out and just start banging away until the sample comes out.
When we're looking at rocks, trying to understand if they preserve evidence of life, we look for things in the rock that cannot form without the influence of life. They can change the chemistry, and they can actually change the shape of the ground. And they can make things like peaks and domes that are sometimes unique to the biology.
Again, I think here what you need to do is look at the context of the rocks around those stromatolites and try to get a sense for what that geology is telling you.
This is our sample here. Came from the outcrop. We've got that new sort of cut and polished face there. And if it was really a cone-shaped structure, then you shouldn't see it on the back of the sample. You shouldn't see it in the back of the hole there. That's about 14 centimetres depth hole, and you're still seeing the structure there. So it's not a cone, it's a ridge. If you can sort of reconstruct that in your mind. You've got to prove the three-dimensional morphology. Absolutely have to prove. It's the same story. You can see the structure at the back of the hole there. It's maybe 15 centimetres or so. It was present at the front and it's present at the back, so it's at least that distance in length. It's not a cone shape at all.
A lot of times when you're looking for something that's related to Earth history, I think of it as being like I'm a detective and I'm looking for clues. But the thing is that the rocks are not very good at preserving clues. And my job as a geologist is to take those little bits of information and see if I can make a story about what happened in the rocks. Part of making that story, though, is understanding the uncertainty. The story is never complete because you're always missing a lot of the clues because the clues have just been lost through time.
After investigating the site thoroughly, the team concludes that there is insufficient evidence of life in these structures. However, there is still much to learn from the geology in this environment.
The rocks that we're looking at here in Greenland are similar, if not identical, in age to the rocks that we're going to be exploring with the Mars 2020 rover. We'd like to think that we can use the lessons that we take from studying the Earth's geological record and apply them when we start exploring the geology of Mars.
One of the really interesting things about searching for life on other worlds is, as a scientist, I have to actually, when I'm looking for life anywhere, I have to actually have a model of what I'm looking for to help guide my observations. And so by looking at these places that are very difficult to interpret on Earth, we get that practice and experience of how do we look at something and what are the questions that we need to ask and what are the observations we need to take to be able to answer them.
Any claim that is made about a biosignature on Mars is going to be debated. So I think that this workshop gives us an opportunity to exercise our ability to have civil disagreements over matters of scientific importance, because I think we're going to be doing much of that with the data that comes back from Mars as well.
I think seeing the rocks in the flesh is just so important. Can't do that for many people, so I think the next best thing is to try and recreate that in a virtual terrain sort of field trip kind of thing. That's what we're trying to do.
So OnSite is an application that we developed for the Mars Science Laboratory mission to help the science team that works with the Mars rover understand the context of the environment around the rover.
And it provides scientists the ability to basically meet on Mars. So it's taking Martian data down from the rover and using photogrammetry to stitch it together to create a 3D model of the outcrop. And then scientists involved in the mission and engineers as well are able to use that 3D model, enter the terrain and make decisions with a much better understanding of the context. We're also using LiDAR imagery out here, which is something not available on Mars. So that's using a laser scanner to basically three-dimensionally scan outcrops and get higher fidelity data so that we can get some very accurate information.
Yeah, so this is the map of the primary outcrops and the laser scans. This is the A outcrop here. There's the flag, there's the cut of the rock, and the other cuts. Now on Mars, it's a different scenario because we're limited to the instruments on board the rover. The rover doesn't have LiDAR. It'd be great if it did. So all we have are the 2D images to work with. 3D reconstruction from 2D images has been part of the Mars missions all the way back to Pathfinder in the late 90s. But it's always been on a per image basis from one rover position. So one of the innovations in OnSite is we started combining rover imagery from multiple rover positions. So if the rover's parked next to a rock and the next day you drive around the rock, you can take imagery from those two positions and get a more complete model of that rock than from any one position on its own. And the holy grail of this is to take all of the rover drives from landing to the current position, register them all together so you could walk from the landing site to the current rover position, seeing high quality 3D imagery all the way. So OnSite was started in the context of the Mars rover missions, but the capability that OnSite and tools like it provide is really, it's a virtual presence and situational awareness in an environment that's hard to visit. Mars is an extreme example of that, but where we are today in western Greenland is not quite as hard to visit as Mars, but it's certainly not easy. So you can imagine geologists going into the field to these remote locations and bringing back not only their written field notes and photos, but a 3D capture of the environment that becomes kind of an immersive field notebook that they can revisit, they can share with their colleagues and with the public and help to communicate what that environment is like in a way that's really hard to get without actually being there in the field. So I don't think this technology ever really replaces a human in the field. Whether or not humans will go to Mars is not my expertise. But if and when humans do go to Mars, only a select few will go to Mars. But with this kind of technology, they can bring along experts from Earth to extend their knowledge and share that experience with the public, so the whole world gets to go along, for the ride.
So I've never been here before, and the landscape in this environment is just, my mind has been blown being out here for a couple of days. I mean, the scale of the glaciers, the complete lack of vegetation in this area, other than sort of, lichens and moss, it's kind of an otherworldly place. It's really starkly beautiful. I think in terms of why anybody should care about these rocks, I mean, they are the record of some of the oldest processes occurring on our planet. I mean, there are very few places that preserve rocks this old. And so they're really a precious resource for geologists to understand what was going on the Earth, in its infancy. So it's an important and special place.
I will gain a huge insight into these particular rocks, but it will also increase my understanding of how you actually demonstrate that something is or isn't a biosignature that I will apply in all my other work.
It's the ability to minimize the ambiguity before it even gets to the publication, minimize the ambiguity and minimize the bias. When it gets out into the press, it's going to be that much more considered, that much more robust. I think that's what's the best outcome of this workshop.
NASA scientists continue to develop and define standards of evidence for discovering alien life. And expeditions like this will continue to inform our ongoing search for life on Mars, the solar system, and the universe beyond.